Hello, my name is Austin Peppers. I'm with the University of Florida Department of Electrical and Computer Engineering, and this is my final project on text mining and technical language processing for electrical PDF data sheets. We're going to start by motivating the topic. So, what are electrical component data sheets? These are manuals or catalogs that manufacturers disseminate to allow electrical engineers to locate and purchase parts. They often contain electrical and mechanical information such as temperature ranges, voltage characteristics, current, wire gauge, the list goes on, and each component will have specifics that are part of that component and might not be for other components. So all manufacturers provide data sheets. Many of them are provided in PDF format. That is because they're transportable, easy to manage, and they're accessible on all operating systems. Most people know how to open and read a PDF. They're fairly lightweight, and some of them are not easily parsed by traditional find operations, which we'll discuss later, but some of them are actually images that are not digitally native. They've been converted to images and then to PDF, which removes the text essentially, and you have to do optical character recognition, which we'll discuss a little bit later. These are two examples of electrical component data sheets. This just so happens to be for a Zener diode, which is a common electrical component. And you can see I've cherry-picked the information that's key, and that's the electrical characteristics, and sometimes they have primary characteristics or a features or summary section that gives a synopsis of what the part does or what it could be used for. You can see from the tables that there are values that are the same, so Zener voltage range, VZ at IZ P1, and that actually shows up here on Microsemi's version of the same component or similar component. So form and function replacements are difficult to locate. This is from personal experience. If the component goes obsolete, it can take up to an hour to find a replacement for a part as simple as one of these diodes. This is a fairly simple example. They get more complex as the electrical component becomes more complex. So things like relays, for example, can be a little bit more difficult, especially high voltage contactors. So this is another example. These military spec, mil-spec connectors. This happens to be the D38999 series connector. There are roughly 60,000 combinations for this connector with different insert arrangements, wire gauges, finishes, receptacles, plugs, pins, sockets, and then to add to that, there's keying to make sure that if you have two connectors that are the same, that you can't cross-mate them. So this website has a part number decoder where you can put in the part number. It'll tell you what that means, but this is a fairly rare resource. It's the only one that I've found, and this is something that I deal with on a daily basis in my engineering background. So there's no general tools for breaking these part numbers down, and it can be very time consuming to find this information for ordering. Here's an example of searching. It can be difficult to find related or compatible parts. So for instance, when you buy these mil-spec connectors, oftentimes if they're connected to a cable, you'll need strain relief, which prevents the wires from being pulled out. And in this example, I used the same connector and searched Google for a back shell that is compatible. Sometimes they're called strain relief, sometimes they're called back shell. And you can see Mouser is a vendor. TTI and TE Connectivity, those are two manufacturers that produce parts that are per the mil spec. So mil spec means that it's been standardized by the U.S. military, and they have certain tolerances they have to meet, and they're all compatible. This allows multiple manufacturers to build the same part. But the results are often inaccurate when you search in Google. You still have to open it up, dig through the PDF, and determine your whether it was accurate or if it was not. We'll see this on the next slide. These are the two that were highlighted in the previous slide, and you can see down here in the bottom right-hand corner where my mouse is, the shell size that has been produced by Google are shell size 15 and shell size 18. So two manufacturers, or actually this is a single manufacturer, Amphenol PCV. The Google search has returned two strain reliefs that are different for the same connector, and as a matter of fact, both of these are not accurate. The shell size is supposed to be J or 24, denoted by this red J, and I just know this from personal experience. Like I said, I deal with this regularly, and it can be very frustrating for other engineers who don't have as much experience and extremely time consuming. This is a very common structure that these military part numbers use, and even non-military spec part numbers. They'll contain a series designator and then a fields that describe the particulars about that component. So down here we have the mil part number, and Amphenol actually has their own part number. So that further complicates the issue where you have two part numbers that are actually identical. They point to an identical part, a single part. And this is just for Amphenol. There's countless other large manufacturers of these components, and each of them may have their own part number builder. These are difficult to parse, and the information can be dispersed. So down here in the bottom right, we see that if you want to see the options you have for finishes, you need to go to table 2, and if you want the dash number, you need to go to table A. So that's referencing other locations within the same document, and it's time consuming and requires human intervention to make those relationships. This is an example of another part number builder. We have MS 27467. This actually happens to be exactly the same mil spec as the D38999 that was shown on previous slides. Again, further complicating the issue where you have multiple definitions for the same part. And I want to point out here that insert arrangement, see page 15 through 19. Over here on the left-hand side is page 15, and insert arrangement series 1 is, these are the options that you have, and they go on, there's about 100 of them, and they say, okay, there's 6 22 gauge contacts, or some of them even have, for instance, 8 20 gauge and 4 16 gauge, and you have to build these part numbers up from scratch. Oftentimes it's very difficult and time consuming. So what we are going to do is generate a framework for extracting the information from these data sheets so it can be stored and later retrieved by an information retrieval tool that's been trained specifically for technical parts. So one piece of software that I'll demonstrate is Camelot, and it's used to extract tables in Python. It does a great job of determining what is a table and pulling that information out, and you can store it in a comma-separated values spreadsheet, and you can manipulate it using other programs like Pandas is what I use, the Python package. But it can also return information such as your X and Y location of that table, and this is part of the feature extraction section, which we'll discuss a little bit later. I manually built a part number builder that essentially uses the rules established in that previous section that I showed and rebuilt all the possible combinations for this one connector. And that's how I know that there happen to be about 60,000 possible combinations for this one connector. It requires extensive manual coding for a single data sheet. It takes a long time just to do this once, so we want to train something that can do this for us. On the left-hand side, we have the PDF original, and on the right-hand side is after the data has been extracted using Camelot, and it's shown in a pandas data frame. So you can see that it does an awesome job of determining what is a table and placing values in the appropriate cells, leaving cells that are blank blank, and it extracted tables with actually from my case studies, it was 100% accurate. It does a great job. It does some formatting where this insert arrangement has been merged across these cells, and it places the information lower leftmost cell, which is actually how CSV files encode the information. So moving to the next slide. This is just an example. This is how the Camelot tool reads through each individual line, and it highlights it in blue as it goes through. How Camelot works is it looks for it looks for vertical and horizontal line intersections and labels that as a point, and it finds the points for each box, and then it finds the information inside and assigns it to that cell. This is another one that it determined was a table, and it is a table, a different style table, and you can see it does a pretty good job of placing things in their appropriate location. Does some strange formatting up here at the top, you can see, but all in all, it's a good tool to use for extracting tables from PDFs, and because tables are such a common part of electrical component data sheets, this is going to be our bread and butter for feature extraction and text mining. Now we have the text portion of the manual extraction. So for this, we use PDF Miner 6, which is a tool that will extract information. It'll extract the text and information about that text. How it works is it performs optical character recognition on the PDF, where it reads line by line and determines what is a character, converts it into a standard ASCII character. It can even do things like plus signs, minus signs, and some other special characters. What it can also return is XY location of text, length of the text blocks, and it can even do font information such as font size, font name, Times New Roman or Arial, and these can be used as features for the future steps of training a model to determine, this is for the technical language processing part of this, to determine what is important or what is key information and what may not be key information. Still doesn't give searchable information, but does provide feature extraction. I'll do a demo of the extraction in a minute. So feature extraction, we are trying to extract text from data sheets for technical language processing. Technical language processing is a subset of natural language processing that's targeted to domain-specific applications where the information is highly technical. I'll go into that again a little bit later in more depth. So features that we can extract include the text chunks, size of the text blocks, font size, location, and then the tables, table name, column names, row titles, units, if applicable. These are just things that are standard and come up time and time again in these electrical component data sheets. So here's an example of the text and feature extraction. So we can see here we have the location, and this is in XY coordinates relative to the page, is the text interfacial pin insert seal, and the font name. It's presented a little bit in kind of a strange manner because I didn't want it to return each character's font name and font size, so it only will return it in strings of 10 characters. So you can see we've got Myriad Pro, semi-bold, font size, and then so even though it doesn't show them as different fonts in the text extraction, we can actually rebuild them based on this information down here. So pretty powerful tool. All right, part 2, technical language